This is Lab 3, Constant Velocity Motion. My name is Nara Roach, and I'm in Physics 221 Lab Section MO2. So today what we're observing is a rolling soccer ball. And so our desired result is to use the momentum principle and the F net equals 0 assumption to try and create a model that will predict the motion of a soccer ball that moves along the ground in the positive x direction. So you can see right here, I have the mass of the soccer ball, which is 0.43 kilograms. As I use a size 5 soccer ball, so I looked it up on the web, and that's the mass. And so the initial position is negative 0.00027 meters, so it's essentially 0. That was just based on where I clicked as the origin. So I have my initial velocity is 6.334 meters per second. So I obtained that by the formula that the velocity is equal to the change in r, or change in position, over the change in t, which is the change in time. And that gives me a velocity of 6.334 meters per second. So here, let me show you the video. So here I have my roommate and one of my friends. They're kicking the soccer ball back and forth. As you can see, I have the axes right here. Here's the x-axis and the y-axis. And I have the origin set to be the center of my soccer ball. So I also have my calibration stick right here, and that is set to 69 centimeters, which is the diameter of a size 5 soccer ball. As the video plays, the ball moves across this way, and that is in the positive x direction. So in order to try and model this using Python, we use the momentum principle. So here we have the equation, and it's the final velocity is equal to the initial velocity plus the net force over the mass times the time interval. So since we're moving in constant velocity, the final velocity must equal the initial velocity. So in order for that to be possible, the net force acting on it must be 0. So that will cancel this term out, and it will leave the final velocity to be equal to the initial velocity. So here I have my setup. And here's my initial conditions. I have the mass of the ball, and I have the initial position, the velocity, and I have the start time. So my time step is going to be 0.01, so it's relatively small compared to the actual time video, which is going to be about 1 second. So here my force vector. So it's 0, 0, 0 in all directions, and here I have the equation to predict the new velocity, which is drawn out right here. And I have also an equation to try and predict the ball's position, which is the initial position plus the ball's velocity times the change in t. So now let me show you the model. So you can see the ball starts at the origin. As it moves away to the left. And here's the graph. As you can see, it has a constant slope, which means it's constant velocity. So now that we have it modeled, let's check out the graph created from it. Here's my graph. We have a time on the x-axis and position on the y-axis. And here the blue dots, they represent the observation data, which is taken from the tracker video. And here the red dots, they're the model data, which is taken from the model, which is created by the model. So as you can see, the red dots, they fit the blue dots really well, which means our model was very good at predicting the motion with constant velocity. So now for the what-if question. If a different origin were chosen, then the only thing that would be different would be the position vectors. Because as you see right here, the initial position would be negative 0.00027, 0, that would be different. But as you see from the formula, where the ball's position is, it doesn't affect the velocity, so it wouldn't affect whether the ball travels at a constant velocity. So for what does it mean? Well, is it possible for you to say how many pushes or pulls are added together to give 0 net force in the case that you observed? Well, I'd say yes, because as you see in the video, the ball is traveling along the ground, so the normal force exerted by the ground up cancels out the force of gravity created by the earth, and so the initial force of friction is canceled out by the force of his foot kicking it. As it moves along, the force of friction is so small it's negligible, so essentially the force acting on it would be constant. Other than that, there's no other forces acting on it, and so the only force acting on it are all canceled out, so that's why we're able to determine that the net force is 0.